Let me start by explaining that context. By the way, my name is Denny Lee. I'm a senior staff developer advocate. Sorry, I forget my own title. I'm a longtime Spark contributor, MLflow contributor, and a Delta Lake maintainer. You should introduce yourself too.
Hi, and I am a staff software engineer. Had to make sure what I've written. I've been working on Delta for the last 5-6 years since its beginning. Before that, I've been working on Spark structure streaming for getting close to 12-13 years now. So been around and ready to ask me all the hard questions.
Yes, because I don't know anything. But also, TD has not played up the fact that he also is the reason we have streaming in the first place. So it was his paper, and it was his development that why we even have streaming, Spark streaming in the first place. So there we go. All right, so lots of logos. Do not worry, I'm not making you have a test here. Okay, so. And don't worry, the slides will actually be available, so you don't have to take pictures if you don't want to. Carly, sorry. Delta Lake has a fantastic ecosystem, as you can see here. Okay, so we have basically the protocol. We have Delta Standalone, which actually covers a lot of other systems like PrestoDB, Hive, Pulsar, and so forth. We have the Delta Rust system, which includes Ballista, Data Fusion, Polars, and so forth and so forth. Right? We have a lot of these different ecosystems that are all working together, all to work with Delta. What does that mean? That means if you're using Trino to run a query, and it's writing data into Delta Lake, and you're also trying to get Flink to write to Delta Lake, and you want to have Spark try to query at the same time, if we all follow the same Delta protocol, all this will work seamlessly, and you don't have to do a single thing about it. Cool, right? Yes? All right, so now, the problem is this. We have at least 8 different implementations of the Delta Lake protocol. Okay? So in other words, and why do we have that? Can anybody guess why? Just to get the crowd in here. Anybody guess why we have at least 8 different implementations? Sorry? Oh, different languages? Yes, that's absolutely true. The different languages is a good reason why. Anybody else want to guess? So he said there was an internal versus internal closed versus an open source one. That would be correct 5 years ago. So, but that's no longer the reason why. So yes, but 5 years ago, that's true. Actually, I have to admit. Okay. Anybody else want to guess? Definitely executors. But I'm going to give you a hint. We actually colored the circles on which one of the different ones. So can you guess, based off of this information, why we have different implementations? Different teams. Presto team is building their own. Trino team is building their own. Flink is building their own. Ray and Dask aren't talking to each other, right? They're building their own, okay? Now, the context is that each time, and TD will go through this, that we go ahead and run a version of the Delta protocol, they have to do every single bit of it. In other words, take the metadata, read the metadata, process it, grab the files, process the files. They have to build their whole implementation of that. Does that seem inefficient to everybody? The guess is yes. Okay, cool, all right. So what we're trying to do is to figure out how to simplify the maintenance of these systems. Because if you want a lakehouse format that can go across multiple different engines and multiple different languages, the goal is that we want to simplify that process, that you don't have to be aware of what I just said, right? Do all of you love to know about these details? No, just in case you haven't figured. Okay, cool. All right, so now that we've called out maintaining this is too complex, 8 different implementations, how do we go ahead and do this? Now, remember, we've had about 5 years or so, just as the gentleman had called out, okay, in which we've had a lot of really good lessons from working with the community, okay? So we have this open protocol, which is great. It's documented. It's all marked down, so you can look at it. You can change it. In fact, anybody who's ever worked with the Delta protocol, they often will come back to us and tell us, oh, there's a problem with the protocol here, here, and here, and then we'll change it, and we'll adjust the code base accordingly, okay? But we have to make it easier for everybody, just like we called out. So let's start with this process. In the end, underneath all the covers, this is just a quick review of what Delta is, okay? It's basically allows you to have scalable storage for your data and a scalable transaction log for your metadata. So you, for example, if I'm going to just pick on Trino just a sec, I think is a really cool project, okay? You would have to go ahead and try to figure out how to scale the transaction log for the metadata, okay? You have to build your own. So does Flink, so does Presto, okay? We're trying to avoid doing that. All we're doing, remember, scaled storage is basically this idea that we have paths to these Parquet files, okay? And the transaction log, the path to these metadata files, these JSON files that contain the Delta Lake transactions. That's it. So theoretically, wouldn't it be easier if we just had one system that took care of all of this, as opposed to every single instantiation of Delta Lake building the exact same thing over and over again to simply give you a list of files? Okay? And so again, the transaction log commits. If I do an insert or if I do an update, cool, we update the transaction log. Again, similar idea. It's just a set of actions. It's the same whatever language you're using. If I'm going to use Delta Rust, if I'm going to use Trino, it's the same set of things. I'm going to access a JSON file. It'll tell me what files make sense for that table and what files no longer are needed for that table. That's it. All right, now skip that. It's fine. All right, so let me switch over and give it to TD on how to build a connector.
All right, thank you, Denny. So let's walk through the life of a developer who has to build a connector for Delta. And this is, you already saw 8 different implementations. Every developer who had to go through those, building the 8 different implementations, had to go through this, so that we understand the pain of doing this. So at the very bottom, we have, in the file system, we have the log files, and then the Parquet files. So step 1 for the connector is to first read the log files, those JSON files you saw, to understand what are the actual Parquet file names that is present in the Delta table right now. So for that, you have to parse those log files, you have to parse JSON. There's also Parquet files as checkpoints inside the log directory. So you have to read Parquet files as well, Parquet log files. You have to replay the log that, just like we saw in the previous thing, that different transactions may actually add and remove files transactionally. So either you have to basically resolve that, oh, this file was added and later removed, resolve all of those adds and removes and figure out, okay, this is the final list of files that are active. So you have to replay the log, figure those out, what are the active Parquet data files. You can do data skipping based on stats on those Parquet files that are also stored in the log. And then finally, once you've resolved the list of active Parquet data files, you give it to the engine, and the engine now figures out how to read those Parquet files. Now, typically, in most engines today, Parquet been around for a long time, this is supported in most engines. So this part, usually connectors don't have to develop that. The engines mostly natively support Parquet reading. Now, to make this part of parsing and reading the replay log, a couple of years ago, like in the last 2-3 years, we have done multiple projects. There's Delta Standalone, which some of us build. There's Delta Rust. Delta Rust folks built by folks sitting in the room here. What they did is we simplified the process of parsing the log, replaying the log, etc. So this chunk of code is written that can be reused by connectors. And so it made connector builders' life a little bit easier. However, this was not enough, because the Delta protocol is continuously evolving. We are continuously innovating on how to make Delta faster and faster. And to make Delta faster, we are getting more and more, we're defining how to do things better on the data path. Like just dealing with Parquet files is not enough. Whenever you have to modify something, modify a single row in the Parquet file, earlier we were basically rewriting the entire Parquet file just to update one row. That is not good enough. That doesn't make it fast. So we are building these new things called deletion vector. Again, this is all part of Delta 3.0, that you can give it a shot. The idea of deletion vector is that along with each Parquet file, we store an additional vector which says that which rows are valid in the Parquet file and which are not. So that to modify or delete one row, you do not have to rewrite that entire Parquet file. You just write this tiny deletion vector file, which is a very compressed bitmap, saying that, just marking that row as deleted. And so at the read time, you have to take this Parquet file and the deletion vector file and combine that information together, basically filter out those rows that are marked as deleted. So this makes things like deletes, updates, merge much faster. But it also means that the data read path is not that simple anymore. It's just not just reading Parquet anymore. It's just something more. We haven't stopped there. We're doing more advanced stuff. Like as we want to give the users of Delta more information about what happened to every row. Like when was this row added? Which version was it added? Which versions it was actually modified as you updated the row or upserted or made changes to that row. We want to give users lineage of what all happened so that users can identify, oh, this is the same row that was added 5 versions ago, has been changed and stuff. So we're adding more metadata per row, which is basically additional columns having metadata in them about the row, to track row-level lineage. Again, these are things that are affecting the Parquet file and changes how to read those Parquet files, which basically means, this innovation means that every connector that was making the assumption that, oh, we'll just read Parquet file and get done with it, all of them have to change. So with deletion vectors, just walk through that example, the log now stores for each file, it stores additional information that, oh, there is an associated deletion vector file that needs to be read. The log REPL has to be changed. The engine has to now know that, oh, I need to read this additional file and filter the Parquet file data with it. So the entire data path has to change, which means more complexity and stuff. Now think about this. If every connector has to continuously modify itself, update itself for every Delta protocol update, the cost of this innovation in the Delta ecosystem is too high. It's a multiplicative cost that the entire Delta, not just Delta community, but the larger data community is suffering, which is not a sustainable process. What we want is to reach a better way, where we want it to be not multiplicative, but additive. You build each connector by writing the code for the connector only once, and for every protocol update, you should do some modification only once across all connectors, so that all connectors don't need to be continuously changed. That is what led to the idea of Delta Kernel. Delta Kernel is a library that implements the Delta protocol, but and all other connectors will use this library to read, write, operate on Delta tables. So I'll go into the details, but basically from this complicated picture, it becomes slightly simpler. This kernel library abstracts out all the details of the protocol from both the log management path and the data management path. And what it provides to the engine is something like an opaque black boxes. Here, use this thing, send it from your engine to all your workers. Now the workers can just use this black box and metadata information to get back the raw data from the table. So that means that the connector and the engine does not need to understand deletion vectors, does not need to understand what is there in the Parquet files, what extra metadata is. It doesn't need to understand any of that. The engine will just tell the kernel library, tell me how to read the data. The library will give back something that looks like a black box. Connector doesn't need to understand what it is. All the connector will do is send it to the workers. Here, figure out how to read. The workers will again ask the kernel, here is information. Give me back the table data that I need. The kernel will give back the table data. That's it. So let's simplify this picture and dig a little bit deeper on what this kernel library means. So the major feature of this kernel library is that it provides narrow stable API for connectors to build against. So all the connectors need to do, let's say you're trying to read a table. All the connectors should have to do is, here is the path to the table, here are the columns I need to read, here are the filters that you can apply while reading. I don't need the other data. And then Delta kernel gives these narrow APIs for the user, for the connector to actually specify that information, and Delta kernel should ultimately give back the rows that has been based on that specification. Now these APIs will be stable, backward compatible. So from a connector point of view, you develop this connector once using this narrow APIs, and then connector to get access to the latest and greatest features of a Delta table, the connector just needs to update the kernel version. That's it. And the kernel internally will basically abstract out all the Delta protocol details. So inside the kernel, if you peer inside the kernel, kernel will take care of all the reading the JSON, reading the Parquet log files, figuring out how to skip data based on your specification of the query filters, how to read the data in Parquet files, DB files. All of those details are within the kernel, and how to transform the data, et cetera. All of the details are within the kernel. But what we also want to enable that, see, kernel cannot unilaterally decide, here is how I want to implement some of these details that is best for all engines. Every engine has its own infrastructure, own internal details with which you can tune for best performance for that engine. For example, as part of the kernel, would like to read the JSON files in the log, et cetera, but Spark and more performant engines like Spark and Trino, or pick any other engine, may have better implementations of how to read JSON and parse JSON much faster than what a new library can do. So what we want to provide is the ability for each engine to customize the kernel and plug in its own versions of performance-sensitive components.
So let me just add some color to that, okay?
Yes.
Back to the slide, okay? So what TD, I want to sort of emphasize this part, okay? What TD is covering is the fact that by default, we're going to provide you a bare minimum, super narrow API that allows you to read the JSON files, that allows you to read the Parquet files. So in other words, we're going to give you as small of a kernel as we possibly can give you to do the bare minimum work, okay? But, for example, if we were taking a standard JSON parser and we chucked it inside there, it would be significantly slower than if I asked Spark or Trino to do it, because they have better JSON parsers embedded in their engine. So because we're both Spark people, I'm going to pick Trino again as a compliment, not as a knockout, okay? Where because I'm trying to get Trino to run faster, we'll plug in Trino's JSON or Parquet reader inside there. So you have the option to take the exact same kernel, plug in Trino's reader of JSON, Trino's reader of Parquet, so it can go faster. All right? So you have both the flexibility to use another system, yet at the exact same time, we're going to give you the bare minimum, so that way we can keep everything really, really small. Because that way, we're not trying to overload you with 20 different libraries, okay? So if anybody's worked with the Spark ecosystem, you'll notice the fact that we load you. Are we still on SBT 0.13? I think we are.
Wait, so on the Spark side,
yeah.
I don't remember.
Yeah, so
probably still one.
Yeah, so the point is that we're going to debate on this, but the whole point is that you have different older versions of Maven, older versions of SBT, older versions of all these different libraries. We're trying to avoid that problem, okay? So that way, as we make changes to Delta, you can, yes, there's still a default, but you can plug in your appropriate library, so that way you can speed things up, okay?
So think of a different way to think of it is, let's say you want to buy a toy that is battery operated. You buy the toy, you get some batteries with it, great, it works nice, etc. But if you want the toy to work better, you can replace those batteries and plug in more powerful batteries. The toy will work better. That's basically the simple idea, to make things pluggable. And to make things pluggable, basically, we're going to provide the APIs. And so this narrow API that we were talking about, there are essentially two sets of APIs. One is the table APIs. That is where the connectors will mainly interact with, and I'm going to walk you through some examples of that, by which the connectors will specify to the kernel, here is what I want to read, here is my query filters and stuff. And then there's a table client APIs with which the connector can optionally choose to plug in additional better batteries. Again, I'm going to walk through that. But to zoom out, basically what we want to try to achieve is that we want to make it easier to build connectors, simple, easy to build connectors very easily with things that are present out of the box there. So there will be, for these client APIs, there will be default implementations that you can choose to use and get started very quickly. But if you want to get to the next level of performance, or plug in your own special dependency stuff, you can basically replace those batteries by providing your own clients. Let's look at some code, how this all works. So I'm going to talk about the client APIs first. The first line is, here we are starting with the default client, default batteries. First, using those default batteries, let's just see how you can read a table. So this table, the first two lines is table, my table. Here I'm specifying, say I'm a connected developer. I'm specifying the path, asking kernel, give me the table for this path. And then this table object is basically represents a conceptual Delta table. And then I want to query a specific version of the table. That's where I need to say to kernel that I want to query the latest snapshot. This is a consistent snapshot view of the table. So there I'm defining what is the snapshot. Give me the latest snapshot. Note that the table client that I defined earlier, which we'll get back to, is the one that is being passed on in all the places, because the table client is the one that the kernel will internally use to figure out how to read JSON. Do I use the default one as I'm here, or I'll come back to say how to plug in the custom ones. And then once I've defined the snapshot to query, here I'm going to start planning out my scan. I'm going to start saying that, oh, I want to build a scan, start providing the information of the scan. Like, for example, here is my query filter. I can also optionally say, here are the columns I want to read. And then to provide that, this builder pattern is to provide all that information incrementally, which provides the scan object. And once we have defined that scan object, now we can just simply read data. So when you call this method, what returns is basically a bunch of columnar batches. Like the data of the table is provided as a bunch of columnar batches. Internally, what is happening? Is it Parquet file? Is it Parquet file plus deletion vector? You don't care about that. You just get the data as columnar batches. By columnar batches, I mean the columns are in vectors, and we chose that format. And that is also pluggable, which, by the way, you can choose your own. Either you can choose to represent your columnar batches as arrow or something else. Spark has its own format. Trino has its own format and stuff. But again, everything is pluggable through that client, which I'll come back later.
So we're basically telling you abstraction and pluggable, if you haven't figured that out yet. So.
Yeah. So now let's look at what the table client looks like. This table client is basically an interface, which has a bunch of sub-interfaces. Each of these interface has a particular job. It has a particular role. So the expression handler, for example. Oh, by the way, this is all preview APIs. So these names, et cetera, subject to change, and we want your feedback, the community's feedback, to figure out what is the right way, what is the most expressive way, an intuitive way to express all of this. But basically, each sub-interface here, expression handler, has a job. It handles expressions. So whenever we have to, let's say, operate on rows, like, for example, compute something on the fly, et cetera, this expression handler can allow you to given an expression, let's say some addition, subtraction, that can be applied on in-memory rows already read from the Parquet table and compute it on the fly. This is, for example, used to do the log replay. So the log replay is reading the JSON as columnar batches, and then do the add, remove, cancellation stuff. These are all expressed internally as expressions, and whenever you have to evaluate that, this is the function that the kernel will call, either the default implementation of this or special implementation. Similarly, JSON handler, this is what the kernel will call to read the JSON log files. Similarly, file system client to interact with file systems, listing the log files and stuff, and then Parquet handler for reading Parquet. So given this interface, kernel will provide a default implementation, which will have its dependencies. For example, for the kernel Java version that is part of Delta 3.0, the default implementation of this table client API uses the Hadoop file system and Hadoop Parquet MR and stuff, which you can use out of the box to build the simple connector. And that will be able to talk to S3, all the standard Hadoop ecosystem stuff like S3, Azure, et cetera. Or if you want to take it to the next level, then you can start in a piecewise fashion replacing some of these sub-interfaces. For example, you can have one custom table client for your connector where you know that you have a better Parquet reading implementation. So you replace only the Parquet handler, but keep all the other, reuse the default ones for expression handling, JSON parsing, and stuff. Or for something else, some other connector, you know that, oh, you have a much better expression management that is better, that is native, or something like that. You can evaluate expressions much better. You can replace the default expression handler with that one and leave everything as a default. So connectors has the power and the flexibility to choose any combination of default and custom implementations to plug in. But the great thing is that all of these changes to take it to the next level, to build a high-performance connector, does not affect rest of the code to define the scan and stuff. So there's a clear separation between the core logic that expresses your computation, what do you want to do with the table, from how do you want to do it, how do you want to exactly do the Parquet reading and stuff. That is all isolated behind the table client interface. So rest of the code doesn't need to change. You just need to replace your default table client with which you started with to a custom table client of your choosing. Make sense?
Yep, definitely.
Cool. So now, this was all theoretical, and we want to really prove that this is possible. This sort of abstraction is possible. So as a proof of concept, we built a Trino Delta connector from scratch. Now, there is an official Trino connector in Trino project, etc. We're not intending to replace that with ours and stuff. We're going to work with them to get the Delta kernel support within that. That is where we're going to work with the Trino community to get this working. But this is just a proof of concept to see whether all these claims I'm trying to make for the last 20 minutes actually works or not. So we built a Trino Delta connector, built from scratch on top of Trino 4.11. If you want to look at the code, there is the link over there. It's on GitHub. It's all open. But not just we use the default client, we actually extended to a custom Trino client where instead of using default Parquet MR to read Parquet, we actually hooked into Trino's existing Parquet reading code path, which obviously is better than some generic external library.
Show them the numbers. Show them the numbers.
Well done, well done. I'm going to show them the demo.
Okay, fine.
We build this. I'm going to demo this.
All right,
and if you are not tired of seeing demos in the summit,
all right, fine. Show
that's
them
your
the
problem.
demo,
Show
and then we show them the
I promise
numbers.
it'll be 5 minutes.
I'm just saying, show them the demo, show them the numbers. Come on, man.
Okay.
Jeez.
Okay. So I have Trino running here. I'm going to start the Trino server. Oh, it's already running. That's fine. By the way, everyone at the back can see. Scream if you cannot. Oh, great.
Well,
Thank
actually,
you.
if you can't see, just come up. Come on. There's plenty of seats. Jeez.
They are scared of us.
I know. It's your fault.
Okay.
As a reminder, since this is a recording, this is a proof of concept. We are going to work with the Trino team. I know you said it, but I'm just going to repeat it again.
Yes. Okay. I have Trino running. This has basically Trino plus the Trino Delta connector built on top of Delta kernel. And then on the other side, I will have PySpark 2.4 running with the latest Delta 3.0 RC that came out today morning. I'll have this running. So what I'm going to do first is I'm going to clear up my space so that I can create a Delta table from scratch. OK. Now, some people are bold enough to write code from scratch using fingers. I am not bold enough for that. So I'm going to just copy-paste stuff here.
Ah, lame-o.
So first of all, let's make the Spark shell less noisy. OK. Oh, actually, I have history. OK, great. So first up, I'm going to take a Spark data frame created from Spark range 0 to 5, just 5 rows. I want to write it to a Delta table, which has only one Parquet file. So I'm repartitioning it to 1, writing to the Delta table, temp/delta. It's working, doing something. OK, let's see. /temp/delta. Oh, this exists. Great. Let's look at what is inside it. OK, this is what I was talking about. So there's a directory delta log, which contains all the log. Let's look at what is inside the delta log. This is that JSON file we were talking about. This contains all the metadata information and stuff. And then the one Parquet file that it wrote out is basically this. So this will have 5 rows and stuff. Let's verify actually that it actually has the content that I wrote out that's arranged from 0 to 5. But let's verify it with Trino. So Trino, I'm going to run this using the Delta connector directly on the path /temp/delta. And yes, there are 5 rows, 0 to 4, as expected. Thank you. Thank
No
you. I felt that
Yeah,
internally.
no, internally. We
Yes,
had to
yes.
get it out of our system.
OK. This is boarding. Now let's do something interesting. Let's pick up one of the absolutely newest project from the Delta Spark side of the implementation, and which we are still not completed building. So called the deletion vector stuff that I talked about earlier. Let's enable that. So let's say I want to delete one of the rows, the ID equal to 0. So I want to delete this 0. Now, to enable deletion vectors, you have to enable it because since it's still work in progress, it's still in preview. It's not enabled automatically. So for that, I have to enable it. And to enable that, I'm going to use SQL alter table for that. So alter table, giving the delta path. I'm setting table property, delta.enable deletion vectors equal to true. That to let the table know that you can use deletion vectors, experimental, but let's use it. This is not writing any Parquet file. Let's double check that. There's still only one Parquet file, but if you look at the delta log, there are now 2 JSON files. This is version 1, so it updated the table, where the only thing it updated is it stored the table property that, oh, this table property has been set. So that next set of commands is going to use the table property. Let's just double check things are fine on Trino. Yeah, still 0 to 4. Okay, this is getting cut off. Okay, cool. Now let's use the deletion vector. Let's delete ID equal to 0. Normally, without deletion vectors, this would replace that one Parquet file with a completely different Parquet file having 4 rows only. But because we've enabled deletion vectors, let's look at the log directly. It has written out a 02.json, the version 2. And now if you look at the base directory here, there's a deletion vector file. This is a binary file containing a compressed bitmap. The same Parquet file as before is still there. That has not been rewritten. But on the Trino side, when we query it, Trino, using Delta Kernel, is reading the Parquet file. Kernel is filtering it out. The connector does not know that it needs to filter out anything. It doesn't have no knowledge of the deletion vector stuff. Kernel is hiding all of the details, and 0 row is deleted. Now, all of this is great. What advantage does it give the connector developers? So in total, the lines of code we wrote across to make this demo possible is around 13,000 lines of code, of which 10,000 is the kernel. So that means the Trino connector is only 2,600 lines of code. And this is Java, so 2,600 lines is probably 100 lines in Scala. So,
and 5 lines in Rust.
Yeah.
I'm sorry, did I say that? I'm sorry.
Yeah. So that means that this a massive amount of code that you don't have to write if you're building a connector. That is the advantage of Delta Kernel. And second advantage is that the connector code did not have to change when we added deletion vector support to the kernel. So now, zooming out, right now with Delta 3.0, we released a preview, an API preview version of Delta Kernel implemented in Java with only read support. But we want to keep extending that for append and update and all sorts of write support stuff. In parallel, we're working with the Delta Rust folks to build the Delta Kernel Rust version of it for the Rust native and Python ecosystem and beyond, to enable connectors that we are not even thinking about yet. And in parallel, as we start having kernel versions of kernel released, we're going to work with the rest of the connector ecosystem to make sure that we help them migrate different connectors on from whatever their native implementation has been to the kernel, so that they get basically to help them rip off their band-aid of maintaining Delta for the future once and for all. So we're going to start with the simple ones like Standalone, Flink, things we've built till now, but we're going to continue working with different ecosystems for that. So this is my final slide. If you have to have clear takeaways, you have to remember two things. I know I have 3 points, but even better, 2 things. We provide APIs that is simple yet pluggable, and you don't, as a connector developer, you don't have to worry about any of the protocol details in the future. And give it a spin with Delta 3.0. Thank you.
That's it.